Hi, this is Nick Bertozzi again. We're continuing our series of videos on linkages. Just to briefly review some of the things we talked about last time. We talked about how the different links could either be in pure rotation. In other words, they had a fixed pivot and just rotated about a fixed point in space or on a robot, and then they could translate. So in other words, not rotate at all, but be able to translate either up, down, left, right, back, forth, or they could be in complex motion, where they were both rotating and translating, which is normally the kind of motion that a coupler in the linkage executes. So we looked at some position synthesis using a graphical technique that allowed us to determine the pivot points and the lengths of the links to achieve a certain position and orientation of the coupler. And in this video, we're going to apply a technique called the instantaneous centers in order to determine velocities at various points in a robotics application. So, for instance, in this example, the link that we're referring to is ABC, which is the mechanism or the component that actually picks up the balls. That's actually a coupler in this 4-bar, right? The robot itself would be a ground link, so that's the 4th link. And the other two, one would be the follower or rocker arm, and the other one would be the crank, which is where you might have some gear assembly that you put on that to use a motor to move that crank up and down. And actually, either of these, the links, either the ones that are connected to the robot base itself, could be a crank. Often it's advantageous to use one over the other, but we'll get into that in a later video. So what we'd like to do now is look at this coupler, which is this L-shaped piece, ABC. And what we would like to do is to be able to determine the velocity, both the magnitude and direction of velocity at point C. So we have a technique that we're going to use to do that velocity synthesis called the method of instantaneous centers. But first, let's talk a little bit about motion in general. This motion is plane motion, which means that the components all move. If you're probably familiar, like with the XY plane in a lot of your math courses. And so, in other words, all the parts move. The motion is all within that plane, even if the links themselves may be offset, at different distances from that plane. All the motion is in the direction of the plane, or in the tangent to the plane, I guess would be the best way to put it. So, with regard to the reference frame on the robot, there are 3 possibilities in planar motion. You could have a body that just rotates, so it's fixed. It has some fixed pivot point, and it only rotates about that point. Or you could have like a slider mechanism that only translates, doesn't rotate, only translates. Or the coupler, in general, has complex motion. It both rotates and translates. So first, let's talk about how to determine the velocity on any point on a body that's rotating. So if you have a body that's rotating about some pivot, and you look at a point, so for instance, in this example, suppose we look at the link that would be connected at point A on the lifting mechanism, which is our coupler, and the other end is connected to the robot. So that's fixed at the pivot point on the robot. And to determine the velocity at point A, if it were rotating counterclockwise, then the velocity in the orientation that it's in right now would just be perpendicular to the radial line that goes from the pivot point out to point A. So right away we know the direction of the velocity. It can't be towards the pivot point because it's a rigid body. So if it moves, it's going to move perpendicular to that radial line from the pivot out to the point. And we can calculate that tangential velocity at that point by simply multiplying the radius times the angular speed. The angular speed would have to be in radians per unit time to do that. So that allows us to quickly determine the velocity at any point along the link. In this case, we're interested in point A. And we could also do the same thing with the link that connects at point B back to the robot. So that would also allow us to determine the direction of the velocity, and that would also be related to the angular speed of that link that goes from B back to the robot by the same equation. It's just going to be that length of that radial line times the angular speed of that particular link. Now, if you have a body that's moving in complex motion, the radius of curvature is not constant, nor is the location of that pivot point. As it turns out, it can be shown that for any rigid body moving in planar motion, even if the motion is complex, there will be a point about which that object is rotating at a given instant. So in other words, that point may or may not be on the body itself, but you can figure out where that instantaneous center is, and that point moves, so you can't use that point, for instance, to determine accelerations, but you can use it to determine velocities of any point on that body. So the way that you do that, based on the simple rotational motion of the link that goes from the robot to B and the link that goes from the robot to A, we can determine 2 points on the coupler ABC where we know the direction of the velocity. Okay? The direction of velocity will be perpendicular to the 2 links, or to the 2 radial lines on those links. If we continue those lines, they will intersect at some point. Now, the important thing to realize here is that the links where they connect at A, the velocity of that link at A is the same for both the coupler and the link that connects back to the robot, because they're connected by a pin, right? That pin has the same velocity where it's touching the link that goes back to the robot and where it's touching the coupler itself. Okay, so if we extend that line, that radial line out that passes through A, and then also extend out the radial line that passes through B, they will intersect at the instantaneous center for the coupler. And those velocities, as we just said, will be the same. So that means that the rotational speed of the coupler can be determined. If we know the rotational speed of the crank that connects from the robot to point A, then we can calculate the velocity, the tangential speed at A. Once we have the tangential speed at A, if we know the distance back to the instantaneous center for the coupler, we can then calculate, because that velocity has to be the same, we can calculate the angular speed of the coupler. Okay? Once we have the angular speed of the coupler, of course, we can also calculate the speed at B. Now, if we wanted to, we could then, once we have the tangential speed at B, we could then calculate the angular speed of the other link that connects from B back to the robot. But in this particular example, we're interested, we're going to say what we really want to know is the velocity, the direction, magnitude of velocity at C. So as can be seen in this diagram, once you have the instantaneous center, you can now draw a radial line out to C. And because we knew the velocity at A, we could calculate the angular speed of the coupler ABC. And with the distance from the instantaneous center to point C, we can now calculate the magnitude of the velocity at C. And we know that the direction of the velocity at C will be perpendicular to the radial line drawn from the instantaneous center out to point C. So this is a very powerful technique that's very easy to use, but we can find, once we have that little bit of information, the location of the instantaneous center and the rotational speed of the coupler, we can find the velocity, magnitude, and direction of any point on the coupler. To summarize, in this video, we introduced the concept of a linkage, and we looked specifically at graphical position synthesis for a 4-bar linkage, and also velocity synthesis using the methods of instantaneous centers. In the next video, we'll get into a little bit more depth in the concepts of how to analyze and specify things like mobility and other topics. So see you next time.